Right, so hello everyone, and thanks for being here today. My name is Yudai Fujiwara, and in this session I'll be presenting a Deep-Kernel Treasure Hunt, discussing the automation process for identifying structures within the Linux kernel that are useful for heap exploitation. Okay, so I'm part of the vulnerability research team at Richauka Security, a Japanese startup that specializes in cybersecurity solutions. And over the past 2.5 years my focus has been on developing exploits and conducting training sessions on Linux and Windows exploitation techniques. And my interests lie in low-level technologies, particularly in exploiting bugs and security vulnerabilities. I'm expanding my knowledge into areas like cryptography and web security, so if you're interested in this field, I'd be happy to discuss on this topic during the networking party tonight. Right, so, I also participate and organize captured flag competitions, contributed to events like SecCon, ACSC, among others. And actually, I'll be hosting a CTF named Cake CTF this weekend, and also I'm going to be running a Black Hat CTF next week, so what a busy month. All right, so today's talk centers on heap-related vulnerabilities, such as heap buffer overflows and use after free, which both are memory safety issues arising from improper memory access. So today, instead of covering protection mechanisms or bug detection methods, I will focus on the challenges of exploiting these bugs and the strategies for solving them. Okay, so these are some descriptions of some randomly selected CVs, and both of them are heap related. And when a bug is described as potentially exploitable, it indicates that the exploitability depends on the environment. And the factors influencing the exploitability include the presence of security mechanisms like Azure or stack smashing protections, or it could be the version of the operating system. But I think a critical determinant is the variety and quantity of structures that can be allocated on the heap. In my practice, developing proof of concepts for heap exploits often requires identifying exploit-friendly structures. For instance, structures containing function pointers that could hijack execution flow, or structures with array length field that can induce further buffer overflow. So the aim here is to extract such structures directly from the binary. And I developed a script to achieve this and tested it on the Linux kernel, resulting in the discovery of over thousands potential structures to facilitate exploit writing. Okay, so this is the brief description by my approach, and it's named multis, short for malloc tracker for identifying exploitable structure, which is just a term coined by ChatGPT. And multis, visualized in the dash box here, is a Ghidra script. And when it's fed with a binary, it analyzes the binary and suggests a list of structures that could be useful for exploitation. I will explain the details later, so let's just skip the slide for now. Okay, so multis is versatile and applicable to both kernel and user space programs, such as browsers or routers. However, the purpose of this presentation, for the purpose of this presentation, I experimented with the Linux kernel, which is a sustainable code base, in order to obtain practical results. And during my experiments, I targeted the structures allocated using kmalloc within the kernel, searching for exploit-friendly structures. And you might not be familiar with kmalloc, but I will cover it later too. Now I will explain why identifying such structures is complex and yet crucial. To set the stage, let's review how the heap works within the kernel space. So the heap in the kernel space serves to store data for drivers and the kernel, like the files or credential structures. So assume this box describes the heap. And when a memory request is made through kmalloc, which is a function to allocate the memory, then a segment is carved from the heap. This allocation is depicted figure here. Not only drivers, but also the kernel itself calls kmalloc, and the segment is likewise carved from the heap. And conversely, when memory is no longer necessary, kfree is called to release it. And it marks the segment for potential reuse. So later, if the driver or kernel calls kmalloc, this freed region might be used. And this reuse across the kernel space implies that the heap-based vulnerability in any driver can impact the entire kernel. For example, if you install a vulnerable printer driver, the attacker may exploit the driver to corrupt the kernel, which may result in privilege escalation. And that's why you shouldn't install drivers from untrusted companies. Even if the driver is not malicious, it's dangerous enough. So heap-related vulnerabilities generally fall into two categories. The first is heap buffer overflow, where exceeding the allocated size during read or write access leads to an overflow. And exploitation is possible if a vulnerable chunk is followed by an exploit-friendly structure. For instance, if the segment depicted at the bottom of the figure here has a function pointer, we might be able to overwrite it to hijack execution flow. Okay, so the second one is use after free, where a freed memory segment is accessed by a dangling pointer. A dangling pointer is a pointer that refers to memory that has already been freed. So it happens when the programmer forgets to discard the pointer or mistakenly release the segment that should be still alive. Because the heap allocator reuses segments, freed segments, another structure might be allocated at exactly the same address as the dangling pointer. And if we use the dangling pointer at this moment, we may corrupt the valid structure, and vice versa. So exploitation is feasible if a new exploit-friendly structure is allocated in the place of the freed segment. Okay, so now I'd like to delve a little deeper into the specific heap allocator used in the Linux kernel, which is known as Slab. The internal of Slab is a bit complex, so I'll focus on a few of its key characteristics. One key feature of the Slab allocator is the way it manages memory. Instead of having a one-size-fits-all approach, Slab allocates separate cache lines for each specific size of data. So imagine that you have a variety of boxes, and each designed to hold items over a certain size. And in the context of Slab, these boxes are actually labeled caches such as kmalloc 8, kmalloc 16, kmalloc 30, and so forth. And the number after kmalloc corresponds to the size of the allocation in bytes. So kmalloc 8 is a cache for 8-byte chunks of data, and kmalloc 16 for 16-byte chunks, and so on. And when Slab needs to allocate memory, it pixes the box or cache that's tailored for the exact size of the allocation required. For instance, if a system requests an allocation of 16 bytes, Slab will use the kmalloc16. And for a 32-byte allocation, it will use the kmalloc32 cache. So it segregates different sizes into different caches. Because each size has its own dedicated cache, an overflow in one block, for example, a 16-byte allocation, does not spill over into the next size category, like a 32-byte block. So chunks of different size blocks often reside in completely different page frames. Okay, so Slab handles freed segments through a singly linked list. And when a segment is freed, it's added to the top of this list. And conversely, when an allocation is made, it takes the top segment from the list. So it's adhering to a first in, first out principle. So let's define what makes a structure exploit-friendly. First, we must be able to control the allocation from user space, as we need the flexibility to allocate and free it to craft the structure purposefully. And second, the structure must contain elements we can leverage, like a function pointer that we could craft to hijack execution flow, or elements that allow read-write access, which could be useful for credential leaks or payload writing. And third, and most crucially, the size of this structure should be similar to the size of the vulnerable segment. Because Slab segregates segments by size into different page frames, in order to exploit a heap-related bug, we need an exploiter-friendly structure that aligns in size. So identifying such structure is a pivotal part of exploitation. And many hackers have pinpointed structures that are particularly beneficial for this purpose. So here are some examples of well-known structures utilized in the Linux kernel exploits. So the sequence operations and TTY struct are fixed size structures that include function pointer. And they are often exploited to hijack execution flow. The latter two, setX attribute and the message, are variable size structures employed in use after free scenarios or heap spraying. We can control the allocation too. For instance, allocating a TTY struct is as simple as opening a /dev/ptmx, which then triggers the allocation within the kernel space. So the goal of my research has been to uncover a broader range of such exploit-friendly structures. Next, I will discuss the work related to this topic that has been done so far. Various hackers and researchers have addressed this challenge and shared their findings. Their approaches fall into two main categories, static and dynamic analysis. In dynamic analysis, the kmalloc function is instrumented to monitor allocations as they occur at runtime. So by setting a breakpoint on kmalloc and invoking a wide range of system calls, we can observe the specific allocations triggered by each call. This method let us pinpoint the exact size of allocation and confirm our control over them based on our interactions. However, dynamic analysis has its limits. It cannot exhaustively enumerate all possibilities. Since it's impractical to test every conceivable parameter for each system call, complete coverage remains elusive, just like the limitations faced in the fuzzing. And to achieve more comprehensive coverage, we need to turn to static analysis. And I've come across several works that utilize static analysis, and one uses LLVM paths to identify all allocation in the source code. This technique reveals every potential allocations. But it does not confirm whether the allocation can be manipulated from user space, which means if it can be called from user space or not. The second and third approaches are similar. They both examine the source code or debug information to collect all the structures defined in the program. And these methods also fall short in determining whether the structure can be allocated from user space. And additionally, they tend to flag static structures that are never allocated on the heap, which are not our focus. So to summarize, there are 4 main challenges, I guess, in identifying exploit-friendly structures. Firstly, we must determine the precise size of the structures. And secondly, we aim to identify all allocations comprehensively without missing any of them or flagging superfluous ones. And thirdly, it's crucial to verify whether the structures can indeed be allocated from user space. And finally, we seek structures containing data that can be exploited or controlled. So I will now introduce the methodology I've developed, which I call multis. Multis aims to identify exploit-friendly structures. It operates by detecting structures that are heap allocated and determining the size of each allocation and identifying possible paths to these allocations. The script achieves this by traversing the control flow graph, enabling it to filter in structures that could potentially be allocated from user space, and those that likely contain exploitable data fields, such as function pointer. Right, so let's consider the pros and cons of each approach. Both dynamic and static methods can accurately find the size of our allocation because this is their primary goal. And dynamic analysis falls short in detecting all allocations within the program. And similarly, some static analysis do not achieve full coverage accuracy because they often include static structures that are not actually heap allocated. And since multis work just like an approach used with LLVM1, the coverage is as good as that of the source code analysis. And when it comes to allocatability, dynamic methods naturally excel. And multis does identify paths to allocation, but this alone is insufficient. Even if a path from user space to the allocation exists, it may be inaccessible due to privilege restrictions. So multis cannot discern whether a structure is allocated with normal user privileges. All right, so next, for the exploitability, none of the previous methods performed checks for exploitability. For instance, since dynamic analysis typically involves setting breakpoints on allocation, it cannot determine the nature of the fields within the structure without enough debugging information. And multis attempts to infer the types of each member of the structure, but its accuracy is contingent upon the results provided by the Ghidra compiler, on which it free depends. And lastly, where multis surpasses other static analysis methods is its independence from the source code. While the availability of the source code and debug symbols can enhance accuracy, multis is capable of operating effectively without them. So the diagram again here provides an overview of the multis. It starts by taking the binary as input and then proceeds to analyze the allocations. And ultimately, it outputs a list of potential exploit-friendly structures. If the address of the kmalloc function is known, Maltese can process the program even without the debug symbols. Nevertheless, supplying debug information could yield a more refined output, as Ghidra can analyze a binary with greater precision. Okay, so I chose Ghidra for several reasons. So as an open source tool, it's freely available for use. And Ghidra has a decompiler engine that can be accessed via scripting, making it highly advantageous for static analysis. While Ghidra is indeed a reverse engineering tool that can function without access to the source code, its open source nature means that it's constantly being refined by the community. The last version of the Ghidra offer the compilation result that I think are impressively accurate. And furthermore, scripting with Ghidra to traverse the control flow graph was really simple and intuitive. Okay, so let's delve into the detailed algorithm using this pseudo snippet from the Linux kernel as our example. So initially, our task is to pinpoint the locations of allocations within the code. So these kmallocs. The script searches for every invocation of allocator function, like kmalloc or kmalloc trace and others. And subsequently, we need to deduce the size of each allocation. In order to do this, I employed symbolic propagation. Symbolic propagation is a technique adept at tracking and speculating the values within the variables and registers. And we can ascertain exact allocation sizes when they are constant. And when allocation vary in size, they are simply labeled as variable. And furthermore, we must ascertain whether these allocations can be inferenced from user space. The script achieves this by traversing the control flow graph and enumerating all the origins of the calls. This method effectively filters out allocations that are unreachable, such as those that occur during the kernel's initialization phase. So to summarize, Maltese is composed of three integral components: the enumeration of allocation, and symbolic propagation, and the traversal of the control flow graph. And the script ultimately informs us where allocations occur, and their sizes, and the origins with the control flow graph. Okay, so now it's time to evaluate results. For my experiment, I targeted the most recent version of Linux kernel available at the time. Within the Slab allocator, there are several types of allocations, but my focus was on the kmalloc slab caches, which serves general purpose. And ultimately, the script identified over 1,000 structures. And the figure on the right side details the experiment logs, where you can see the script enumerating the allocations and extracting the sizes of the allocations. The script required approximately 5 minutes to complete its run on my laptop, which I consider to be quite practical for analyzing large software. And due to time constraints, I won't discuss all the identified structures, but we'll highlight a few notable ones. The first example is signal FD context. This structure is particularly intriguing due to its small size. Structures allocated from KMalloc 8 are limited, since most have at least 2 member fields. But signal FD context has only a single field named sigmask. By reviewing Maltese output and tracing the code tree, it turned out that we can control this structure's allocation with user-level privileges. And allocating the structure is as simple as invoking the signal FD system call. And the structure can be released by closing the file descriptor. Initially, this structure seemed useless because it contains only one single 64-bit integer. But we can interact with this value through procfs and manipulate it using sigdel set mask and signat set system calls. Therefore, it could be useful for use after free exploits, as it allows for reading and writing of its data fields. Another example is shared memory ID kernel. There is a structure named shared memory file data, which is already well known in the context of kernel exploitation. However, the script unveiled yet another structure, shared memory ID kernel. This structure comes from the KMalloc 256 cache. And we can manipulate its allocation through shared memory get and shared memory control system calls to cross. This structure contains a pointer to the kernel's data section, which could be useful in calculating the kernel's base address. And moreover, it includes a pointer to the structure called current, which encapsulates comprehensive thread information. Given that current contains a reference to the process credential, this could potentially be exploited to change the process the effective privilege. And additionally, it has a function pointer, which, although challenging, could be exploitable based on my testing. The last structure I'll discuss is a semaphore array. This is a variable-sized entity whose size we can change. By calling a shared memory get system call with specific arguments, we can instantiate this structure in various sizes. The sems field here is an array which can be manipulated to a certain degree. And similar to the previous example, this structure also contains a function pointer, which might be useful for controlling the execution flow. While the script successfully identified many structures, there remains challenges to address. Ghidorah, despite its capabilities, does not perfectly resolve cross-references or of indirect branches. This limitation is not unique to Ghidorah, but is an inherent program in static analysis. And consequently, the precision of the method I propose is tied to the accuracy of the reverse engineering framework. Another obstacle pertains to variable-sized allocations. Programmers often use the heap for its flexibility in handling resizable variables. So allocation sizes frequently vary. If we could predict a range of potential sizes, the result would be more precise. However, such prediction requires intricate data flow analysis that tracks variable values across functions, which could be prohibitively slow. In order to maintain practical analysis speed, I chose to implement only intra-function symbolic propagation, not over across functions. So moving to the conclusion, Through this research, I developed a Ghidra script called Maldies that has successfully discovered over thousands of exploit-friendly structures in Linux kernel. The script is designed for versatility, making it suitable for both kernel and user space applications. It's particularly advantageous for analyzing closed source or complex software, like routers or browsers. Okay, so let's move to the takeaways. Firstly, heap-related bugs are not inherently exploitable. In order to exploit these bugs effectively, we require additional exploit-friendly structures in most cases, such as those containing function pointers. Secondly, vulnerabilities within the kernel space are generally more exploitable and critical than those in user space, given that a single bug can compromise the entire kernel. This holds for both the Linux and Windows kernel. And lastly, the Ghidra scripting framework is extremely powerful. This was my first time to write a Ghidra script. Despite facing issues like incompatible APIs and outdated documentation, the breadth of features within the framework makes it an exceptional tool for binary analysis, I think. So this brings us to the end of my presentation today. I'd like to extend my gratitude to all the staffs at Cold Brew for their hard work, and the sponsors, of course, making this event fantastic. And I must also thank Yuichi for his support in my first conference speech. And OK, so now we'll proceed to the Q&A session. If you are interested in today's topic, my contact details are provided here. And additionally, I'll be attending the networking party this evening, so please don't hesitate to approach me for a discussion. Thank you very much for your attention.
May I ask a question in Japanese? On this slide, the Ghidra script that you mentioned, have you uploaded this to GitHub? No, not yet, but once I'm ready, I will be ready. Is there somewhere that you can find this slide in the internet? I think the Cold Blue would disclose this and make it in the public domain. Hello, I'd like to ask a question in Japanese. When you write Ghidra script, you said that you encountered difficulty because of outdated documentation. What sort of specific difficulties have you faced? Well, it took me the biggest time. It's a symbolic propagation algorithm. So the Ghidra provides a compiler, and one of the engines is a symbolic propagation, which is something like a library, but documentation is quite limited, and even if there is documentation available, it was not useful. So that's the difficulty that I faced. Thank you. So using this script, any news exploit that you found or CTF question that you solved effectively with this script? Well, when I try to solve CTF issue and I have a lot of difficulty, that's why I sought this script in the first place. And I haven't tried this with CB, but the vulnerable driver that was purposefully built for that purpose, and also HitCon. I was not able to use this because of restriction, but there was something that was promising. So I think this could be useful for solving CTF. Thank you very much for your presentation. It's a very local question, but SIM-ID kernel structure was presented, and FCK ASLA is something that this can be used for. But FCK ASLA, from kernel base, so the functions would be separate and disparate. But if you're talking about just KASLA, from the pointer, very simply you can calculate the base. But with the FGK ASLA, how do you do the calculation? FGK ASLA is a function granular ASLA. So for each function it moves, but for one data section, it is not randomized. So if the pointer is looking at that function, then that is the that is used for calculation. But you are not able to solve the calculation. No, not through parse, and other data-oriented attack is used for that.